morning or good afternoon, everyone. This is the first webinar in a series of webinars from Physical Acoustics Interest Group. Our first speaker is Dr. Vicente Romero-García from Institute of Pure and Applied Mathematics at Politècnica University of València. He's a senior lecturer there. Prior to that, he was a researcher at Laboratoire Acoustics at Le Mans University, and I had the privilege of collaborating with him quite a few years ago on some joint projects. The title of his talk is Perfect Acoustic Absorption in Reciprocal Ventilated Problem. And just to remind our colleagues that the session is recorded and will be available in UKAN Plus YouTube channel soon. If you have questions during the talk, please type it in the Q&A, and hopefully we'll have 10 minutes at the end to for verbal questions or questions and Q&A to be answered. Okay, so without further ado, I'll ask Vicente to start the talk. Thank you.
Thank you very much, Sharam, for the nice introduction. First of all, I would like to thank the organizing committee of the this UKAN webinar for inviting me to deliver this talk. It's an honor to me to talk to all of you, and I would like to thank you all for being here in this webinar. And today I would like to talk about perfect acoustic absorption in reciprocal ventilated problems. We talk a little bit about the original works that we have done in that topic, and also in the new results that we have obtained recently. This is a work that I have done when I was in LAUM, in Acoustics Laboratory of Le Mans University, with my colleagues Jean Boulbert, Yang Meng, Wenael Gabar, Vincent Pagneux, and Jean-Philippe Groby, and also with Noé Jiménez, who is now also at UPV here in the other institute in Spain. I would like to say that this work is mainly the work that Noé, Yang, and Jean Boulbert has done during their postdoc at LAUM with Jean-Philippe and myself in LAUM in France. So as you can see in the title of my presentation, there are three important concepts. The first one is related to the word ventilated. Ventilated means a transmission problem. So you have a wave that arrives to an object, and you can have transmission and reflection. There is nothing to do with flow acoustics. It's just that you can have a transmission problem. Reciprocal is the second concept. So that means that I'm in the linear and my system is passive. So I'm in the linear regime. And the third one is perfect acoustic absorption. So I want to study what are the conditions of the system to have alpha, which is the acoustic absorption, equal to 1, or at least the closest to 1. So in that context, I have divided my presentation in 4 parts. The first one is a short introduction to introduce the mathematical description of the problem. Then I will focus on the case of mirror symmetric resonators. Then I will jump to the mirror asymmetric resonator, and in this part I will talk, if I have time, to 3 problems. The first one is the narrow cross-section. The second part is the wide cross-section waveguides, and the third one is the open tube problems. So if I have time, I will talk about all of that, and if not, I will exit from the presentation at some point during this third part, and I will go to the conclusions and remarks of the work. So let's start with a simple problem in which you have a resonator, which is, or an object, which is called capital sigma here, placed at x equal to 0. This resonator is radiated by two incident waves, one coming from the left and the other one coming from the right, with amplitudes A and B. And this resonator can reflect or transmit both of these incident waves, which is the outgoing waves with amplitude D and amplitude C. So this is left going and right going waves to the from the resonator. So this problem can be studied in a general way by using the scattering matrix S of omega, written like this, where T and R plus and R minus are the transmission and reflection coefficients from each side respectively, relating the amplitudes of the ingoing waves with the outgoing waves. Sorry, there is a typo here, should be, but in any case, you have to think that this is outgoing and this is ingoing waves. And here you have the transmission and reflection coefficients. So here you can study the eigenvalues and eigenvectors of the system. And you can notice that if an eigenvalue of the scattering matrix is 0, then this corresponds to the case in which the incident waves can be completely absorbed, because C, in fact, is C and D are equals to 0. And this happens at a frequency at which the transmission equals to this value. When we don't have losses, this appears for a frequency that is complex, so it's not realistic. But when we have losses, this can happen for a frequency that is real, and then we can have the situation of perfect absorption. In a simple case in which you don't have transmission, so if you are not in a ventilated problem, then the scattering matrix collapses to a scalar value, which is the reflection coefficient, and the perfect absorption is just the impedance match problem of the system. And what you want to do is that the reflection coefficient will be 0 at some particular frequency. I will not talk about that because I'm interested in the ventilated problems. And in the ventilated problems, in fact, you have two different kinds of problems. The first one is the asymmetric resonator. Notice that I can have the same transmission coefficient because I'm in the reciprocal problem, but I can have different reflection coefficients in the case of lossy systems, in which the reflection coefficient is different from both sides. And this means that the system behaves in a way which is asymmetric or non-mirror symmetric with respect to the middle plane. So to obtain that kind of conditions, the reflection coefficient from one side equal to 0, we have to accomplish that kind of system. And if you can see that one of the two reflection coefficient is 0, then the transmission coefficient will be 0, and then you can have perfect absorption. The second problem is when the resonator is symmetric. That means that the reflection coefficient from the right and from the left is the same. And in that case, to obtain perfect absorption, you need to accomplish that condition. And to do that, in fact, you need that the reflection and transmission will be 0. Let me start by discussing this system with symmetric resonator. And this is what I call reciprocal symmetric system. So here is the system that I want to study here. This is a panel in which you have slits, and these slits you load, in that case, Helmholtz resonators, and then a wave arrives from the left, and then you have the reflection and the transmission coefficient. And in that system, I will consider the losses by using the Stinson model, which is effective, complex, and frequency-dependent parameters. And I will consider also the correction length accounted for the Helmholtz resonator and for in this problem. So in the experiments that I will show through this presentation, I will use this setup in which I put the resonator in this position here, flash mounted or at the end in the structure. Basically, I will put this and I will have slits here. And I have a robot that can measure the acoustic field in this part of the system in order to obtain the A and B amplitudes. And in the other part of the tube, I have 4 positions in which I can obtain, allows me to obtain C and D. Okay, and I will use an anechoic termination. Here you have the characterization of the anechoic termination, and you can see that in fact it's really working in the range of frequencies in which I want to study the perfect absorption. I will use also what we call the Argand diagram to visualize the perfect absorption from the experimental data. And this is just the representation of the eigenvalues of the scattering matrix in terms of real and imaginary part of them in terms of frequency. If one of the points is close or on the origin of coordinates, this configuration corresponds to the perfect absorption configuration, just to give you this information. So let me start by the mirror symmetric resonator. This case is represented by this plot here. You can see here a full transmission problem. And here you have a wave that is radiating from the left to the right to the system. The system is here represented in black. Then you have the reflection coefficient and the transmission coefficient. And in that case, as the system is completely symmetric, then in fact, the reflection coefficient is the same from both sides. And the transmission coefficient in the diagonal is the same because we are in the reciprocal systems. Okay, so let me just discuss 2 different configurations in which I introduced a Newman boundary condition at the middle plane of my system. Okay, if I introduce this Newman boundary condition, this is like a mirror for acoustic waves. And basically what you have from this mirror is the image from the other side of the reflection coefficient. When we put a Newman boundary condition in the middle plane of the structure, is just the addition of the reflection and transmission coefficient of my original problem. However, if I consider a Dirichlet boundary condition or pressure release condition here, in fact, you have an image with a change of phase here. This is why you have the minus, because this is introduced by the Dirichlet boundary condition. And the reflection coefficient from that problem is just the subtraction of the transmission and reflection coefficient of the original problems. So you can see that I can define a symmetric problem related to the Newman boundary condition, and an antisymmetric problem related to the Dirichlet boundary condition. And you can see that the reflection coefficient of the symmetric problem corresponds to one of the 2 eigenvalues of my scattering matrix here, and the antisymmetric problem, the reflection coefficient corresponds to the other eigenvalue of the scattering matrix. So look, if I want to study the reflection and transmission coefficient of my original problem, I can decompose this problem in terms of symmetric problem and antisymmetric problem in such a way that the reflection coefficient is just that, the reflection of the symmetric plus the reflection of the antisymmetric divided by 2, the transmission is given by that, and the absorption is just given by the absorption of the symmetric plus the absorption of the antisymmetric divided by 2. So if we want to obtain a perfect absorption, so alpha equal to 1 at a given frequency in this kind of problem with symmetry, then we need to simultaneously obtain that the reflection of the symmetric problem should be 0, and the reflection of the antisymmetric problem should be 0. Then, if we have that, the absorption of my original problem is equal to 1. So let me discuss this situation in a very simple case. This is the case of in which you have a slit here of length L. We have the amplitude, the pressure, the incident pressure here, the reflection and transmission. This is a very simple problem. It's just a Fabry-Perot resonator, basically. And you can see, you can study the reflection and transmission coefficient. Here, if you plot the transmission and reflection coefficient, you can see that at these peaks that corresponds to the resonances of the slit, the Fabry-Perot resonances of this slit, you have an absorption that cannot surpass, you cannot pass the value of alpha equal to 0.5. So if now we plot the complex frequency plane, in the complex frequency plane, the eigenvalues of the scattering of the eigenvalues of the scattering matrix, here you have the eigenvalues of the symmetric problem, and these are the eigenvalues corresponding to the anti-symmetric problem. You can see here that I represent the real and imaginary part of the frequency. So I give complex frequencies to my reflection and transmission coefficients, and I plot these situations. And you can see that, in fact, for the symmetric and anti-symmetric structures, the zeros are completely at different frequencies. If you think a little bit on the shape of the modes in the slit, you can see that the first one is symmetric, that corresponds to this one. The second one is anti-symmetric, that corresponds to this one, and so on. So they are not at the same frequency. As they are not at the same frequency, that means that for that problem, only half of the system can be used to obtain absorption. And so if you calculate the absorption of the original problem, the absorption, for example, for this mode here, which corresponds to that one, corresponds to absorption of the antisymmetric, because this 0 is close to the axis here. And here, the symmetric problem is not impedance matched. So you have something here which is close to 1, something here that is close to 0, and that means that the absorption is 0.5. So which is the problem that we have here. So we cannot have more than 0.5 if we use that kind of problems. We can have more if we have another kind of resonator that couples the antisymmetric, in that case, the symmetric problem, in the example that I give you. So to solve this problem, what we need is to introduce other kind of resonators that present at the same frequency symmetric and antisymmetric resonances. This is what we call the generate resonators, because they have two resonances at the same frequency. In that case, what we use is basically this block here, in which we have two slits here. In one of the slits, we load a Helmholtz resonator, and the other one, we load two Helmholtz resonators. In the case in which we load a Helmholtz resonator, we will have asymmetric mode. And in the case in which we load two resonators, we will have asymmetric mode and an antisymmetric mode. So in that problem, in fact, we will consider the losses by the Stinson model, as I told you previously. The correction length of the Helmholtz resonators are also taken into account. But in that case, we consider the several modes, the multimodal propagation in the waveguide, in order to consider the possible coupling between the slits here. Okay, which we will see that it's quite critical in that system. So in order to obtain perfect absorption in that kind of systems, what we need is first to work with the antisymmetric resonator. So let's consider the same configuration, but in which we impose a Dirichlet condition at the middle of the system. In that case, what we have is a change of phase in the image of the original reflection problem. And then what we do is we look for the configuration of the resonators in this part of the structure without touching this one in order to obtain a perfect absorption in this reflection problem. And then, as you can see here, you have a null in this position here, and that means that when we will go to the full problem, this corresponds to the antisymmetric component of the system, because we impose here a pressure release condition in the middle. Then, if we go to the symmetric resonator by imposing here a Newman boundary condition here, so a mirror symmetric structure, then we don't have the change of phase. And we now, once we have fixed the lower part of our system, now we change the geometry of the upper part of the system in order to critically coupled or impedance match the symmetric part of the problem. Notice that in that case, for the symmetric part of the system, the two resonators are excited, because in the lower part, we have symmetric resonances. However, in this part, when we critically coupled the antisymmetric structure, the upper part is not having any important role in that case, because it's not excited in the antisymmetric problem. So once we have obtained the upper part and the lower part of the system, we have to put both at the same structure and analyze the transmission problem. So this is the system that we have analyzed. You can see here, this is a 3D printed structure that we have introduced in our square section tube at Acoustic Laboratory of University. And we have radiated the structure with a plane wave. And you can see here that at 800 Hz, at the frequency in which we have designed this structure, we have a perfect absorption at this particular frequency. You can see that the transmission and the reflection are very close to zero. The difference in the absorption close to 1 is due to the possible errors in the experimental setup. So here you have lines are analytical results by using the multimodal expansion. Crosses are the experimental results, and circles are the numerical results. So you can see here different kind of, you have here the legend. The important thing is that if we plot the absolute value of the pressure at this particular frequency, you can see that effectively in the upper slit, we are exciting the symmetric mode, and in the lower slit, we are exciting the antisymmetric mode. And you can see that for the two eigenvalues, the Argand diagrams are very close to the origin of coordinates, meaning that the system is basically critically coupled or impedance matched, having the perfect absorption. One important point to do that is the effect of the evanescent coupling due to the higher order modes. So if you don't use higher order modes in the waveguide, or meaning you're using, for example, just the transfer matrix method in which you have only the plane wave, then the system is not at all working. So this is important to know, because if you calculate with the transmission, with the transfer matrix, these are the reflection and transmission coefficient, which are completely different to the ones that we want to obtain. And this is why, because the evanescent coupling between the slits is quite important, and we need the higher order modes to design this structure. Okay, so this is all the things with respect to the mirror symmetric resonators. So now let me go to the mirror asymmetric resonators. And let me start by the discussion of the general problem. We have a waveguide, as previously here, in which we introduce two resonators separated at distance delta. And these resonators are characterized by complex and frequency-dependent quantities, which are impedance and wave number. And by using, in that case, the transfer matrix method, you can obtain the transmission and reflection coefficient from both sides. Notice that in that case, with respect to the middle plane, the system is completely asymmetric. And this is why you have a reflection coefficient from the left and a reflection coefficient from the right. The transmission coefficient remains the same from both sides because, as I told you, we are in the reciprocal problem. So in order to obtain perfect absorption in that system, in fact, we need, first of all, we need to obtain transmission equal to 0. So if we obtain transmission equal to 0, we need to do beta 1 and beta 2, at least one of the two equals to 0. We choose, in that case, we choose beta 2. So first of all, we need to cancel the transmission coefficient. To cancel T, in fact, if we are in the lossless case, it's very simple. We put this guy to resonate at a given frequency, and at this particular resonant frequency, the imaginary is purely complex, purely imaginary, and at this particular frequency, the impedance is equal to 0. However, in the lossy case, it's not the case, and you have that the impedance should be very, very small, should be smaller than that quantity. So this means that the impedance that should have this resonator should be depend on the cross-section of the waveguide, the cross-section of the resonator, and the number of resonators. So notice that if the cross-section is very big, then the value of the impedance that you should obtain here is very small. And in particular, this could be difficult because in that case, you will need more resonators in order to increase this value, in order to obtain a value of the impedance higher, because when you go to lower frequencies, the resonators has very small amount of losses, and this is very difficult to obtain. Even in that case, the impedance could be much bigger. So once we cancel T by using this resonator, we need to cancel one of the two, R plus or R minus. So this is the price that we have to pay in order to obtain perfect absorption with asymmetric structures, is that we only can obtain perfect absorption from one side. This is what I said, unidirectional perfect absorption. So to cancel R plus in that case, in fact, you can, if we impose Z2 equal to 0 or close to 0 with a very small value, the condition that we obtain is that equation that we can develop in Taylor. And if you develop that in Taylor, we obtain a minimal absorbent length here that depends on the cross-section of the waveguide, basically. So the cross-section of the waveguide is quite important. And in particular, here, if you are close to the Fabry-Perot resonance of the system, in fact, at these frequencies, you cannot obtain perfect absorption because the system is purely reflective, okay? So here you have to play with the cross-section. So let me discuss that kind of things. First of all, let me start with a small cross-section, which is the system here. And you can see here that I have two resonators with a cross-section here, which is very small here. And in that case, we fix a frequency F1 at which the transmission is completely destroyed or mostly destroyed, because you cannot completely destroy the transmission in a real problem. And once this transmission is very small, then the problem becomes basically a reflection problem. And what you have to do is to fix the geometry of the second resonator in order to obtain the perfect absorption at a given frequency between the frequency F1 and F2. You can see here the transfer matrix results, the finite element results, and the experimental results, obtaining here the perfect absorption at a given frequency. So notice that in that case, in fact, the plane wave approximation is enough to describe the perfect absorption in that kind of system. However, if we study the other side of the system, you can see that the absorption coefficient from the other side is not perfect. And this is the price that we have to pay in order to obtain perfect absorption in that kind of system. So now that we understand how to design that kind of structures, we can repeat this process in cascade. And in fact, now we can, for example, by using two, we have one peak, we can add a third resonator and try to obtain two peaks of perfect or quasi-perfect absorption. You can see here the system, and we can do this for n resonators. And you can see the n peaks of quasi-perfect absorption. And once we have this, we can push the system to obtain a flat absorption. This flat absorption is not perfect, it's not one in mostly any point, is close, very close to one, but the price that we have to pay is that we don't have perfect absorption, but it's very flat and it's very close to one. So we can design that kind of structures, and it's just a play between the geometry and the cross-section of the waveguide, the geometry of the resonator and the cross-section of the waveguides. So we have 3D printed that kind of structures, and here you can see the experimental results in the dot line, and we can see that we have mostly perfect, quasi-perfect absorption from 350 Hertz till 1000 Hertz. The length of the system is 11 centimeters, 11.3 centimeters, which is it's quite sub-wavelength. It's 10, the ratio lambda over L is 10. So this is a very nice result that we have obtained. And this particular system shows that each frequency is absorbed at one particular position in the structure due to the fact that each resonator is designed to absorb each frequency, and this is why we call that rainbow absorbers. So this is published in scientific reports. This is one of the papers of Noé in 2017. But this corresponds to the case of short cross section, short, very narrow cross section. So what happens if we go to large cross section? So I will not go too much into details, but I will show you just several examples. So here I consider a Helmholtz resonator that is loaded to a waveguide, and the height of the waveguide is h, right? So now I study the transmission loss produced by this resonator, and in fact, we optimize the resonator to reduce the transmission as maximum as possible in terms of the height of the waveguide. So you can see that if the waveguide is very narrow, is not wide, so 1.5 centimeters, the transmission loss arrives to a high value and is, let's say, you can say that the quality factor of this peak is quite low because it's wide in frequency. However, if we increase the the heat of the waveguide, you can see that we arrive to a low value of the transmission loss, but the price that we have to pay is that the quality factor is reduced a lot. So that means that the quality factor of the resonator increases as we increase the heat of the waveguide. So this could be a problem to generate broadband absorption with high waveguides or wide waveguides. The other thing that we want to do is to cancel one of the two reflection coefficients. So to do that, in fact, we have to analyze the condition that we have obtained previously, and we have to play with the distance between the resonators. So if the distance is very short, in fact, you can see here that again, the quality factor of the this peak is very high, meaning that the peak is very narrow in frequency. And again, if we want to do something that is small in distances, so sub-wavelength, and with wide waveguides, then we have to pay the price of working with very narrow regions of frequency, right? So taking that, having that in mind, I would like also to discuss the effect of the evanescent coupling between the two resonators, because we have two resonators that are plugged in the system and in the waveguide, and they are close one to the other. So if we study here the transmission loss by using the transfer matrix, you can see here the peak of transmission loss, and here you can, in terms of the height of the waveguide, and here you have the peak of the transmission loss in terms of the distance between the resonators. So you can see that as we increase the height of the resonator, if we calculate the problem by using the multimodal techniques, so using the evanescent coupling, you can see that at high values of the height of the waveguide, so for wide waveguides, this behavior is completely destroyed, and it's very difficult to obtain a low transmission loss. The same happens when we go to the situation in which the resonators are very close one to the other. So when we want to obtain perfect absorption with wide waveguides and closest resonators, so narrow systems, sub-wavelength systems, we are in the bad situation in order to obtain perfect absorption. So you have to push a little bit more the model in order to obtain this perfect absorption. So you have to look for the good configuration. So this is what we have done. We have designed this structure, which is, this is a cross-sectional waveguide in which we have plugged a combination of rows of identical resonators here. And we have optimized the system in order to increase, to obtain the, let's say, the perfect absorption, this quasi-perfect absorption in a narrow range of frequencies in order to take into account all the effects of the evanescent coupling and the high width of the system. So here you have the system that we have 3D printed. This is plugged in a waveguide with a height of 15 centimeters. So here in red line, you have the measurement. You have here the absorption coefficient from the side that we designed the structure to obtain perfect absorption in the range of frequencies here in gray. The finite element methods are shown in crosses here. The dashed dot blue line is the multimodal method here, and the dot green line is the transfer matrix method. So you can see here that if we only consider the plane wave propagation, the system doesn't reproduce, the model doesn't reproduce the experimental results because it's not taking into account the evanescent coupling between the resonators. And here, in fact, you can see that at this particular range of frequencies, the absorption is very close to 1. And here, in order to show you the results, I show you also the transmission loss and the reflection loss. And the main differences between the model and the experiments is possibly due to the rugosity in the necks of the resonator. This is a zoom of one of the necks here in the resonator, and you can see that the walls are not completely straight. So the modeling of the losses in that kind of system could be inaccurate, and this produces the slight differences in reflection and transmission out from the region of the optimization region. Okay, so now this is the last part of my talk. I would like to give you the last results that we have obtained with the work of Meng Yang, which is postdoc now in LAUM, which is doing a very good job in that kind of structures. And now, in fact, we want to modify a little bit the problem. We have a plane wave radiating the system from the right of the system. This plane wave will encounter a region in which we will put the metamaterial in parallel to the waveguide. So the presence of this metamaterial will produce the reflection. And then the tube here is plugged to a infinite rigid wall. So here what we have is a radiation domain here, right? So now we want to obtain a system in which reduces as much as possible the radiation and also the reflection in the system. This is why we call this problem the open duct problem. So you have a duct that is plugged to an infinite wall that is radiating sound to the exterior. And then we want to put here a treatment made of resonators that reduces both the reflection and the radiation. So the radiation can be obtained by the integration of the sound intensity on the outer field surface here. And the expression is given by that depends on the impedance radiation and the reflection and transmission coefficient of the system, right? So the radiation impedance is well known in the books, it's just given by this expression. And the idea is to design a material that is made of rings in which we introduce several identical resonators in each ring, and each ring is different to the other one. So let me study just a single resonator. In that case, the maximal absorption is given by this formula here, which is analytically studied. And we can plot this, this absorption, maximal absorption, in terms of the impedance of the Helmholtz resonator and the length of the Helmholtz resonator to the end of the structure. You can see that, in fact, at low frequencies, we can obtain perfect absorption, but the maximal absorption is bounded, and we cannot surpass, we cannot have absorption higher than this red line in fact, this red line by using a single Helmholtz resonator. So the scatter provides an optimal impedance and an optimal distance, but this optimal will produce an absorption that will be in this red line. You cannot have higher absorption than that red line. So we have designed two examples of this system, and you can see here two rings that produces this absorption that corresponds to the bounds. And if we put different resonators in the same ring, what we can obtain is a broadband absorption, but along the bound. We cannot pass the bound of the absorption. If we want to pass the bound of the absorption, what we need to do is to use two Helmholtz resonators. And if we use these two Helmholtz resonators, in fact, we can manage to design the impedance of the Helmholtz resonator of each one and the length with respect to the end of the system and between both resonators in order to surpass this structure. So we have designed this structure with two rings in which we have this quasi-perfect absorption at one particular frequency, surpassing the bound imposed by the theory. And basically, we can repeat this structure in order to have a broadband quasi-perfect absorption surpassing the bound imposed by the theory. So these are the results that I wanted to show you today. And to conclude, I would like to give you some remarks. So by using mirror symmetric absorbers, we can obtain perfect absorption from the two sides. And to do that, we need degenerate resonators. We need to use the block waves in order to obtain the coupling between the structures. If we want to obtain perfect absorption in a broadband structure, the most simple situation is to use the tuned resonator. The price that we have to pay is that we will obtain only unidirectional absorption from one side. And we can design structures to obtain rainbow absorbers with narrow waveguides, which is the simplest situation. If we go to large cross-section, we still can obtain perfect absorption, but the price that we have to pay is that the range of frequencies will be narrower. And finally, for the up-end duct, we can also obtain alpha equal to 1. But to do that, we need at least 2-point scatterers. So here in bold characters, you have the papers in which you have all the details about the things that I talked today. And I would like to thank you for the attention. And I will be happy if you have some questions, and I will be happy to answer them and discuss with all of you. So thank you very much for your attention.
Thank you very much, Vicente. That was a fascinating talk. Appreciate that. Now, I see that there is no question in Q&A, and if there is anyone wishes to ask a question, please raise your hand and see if I can allow you to talk. Right.
Vicente, can I ask a question?
Sure, Anton.
I will use my panelists
okay.
right to talk. So for the last bit, so where you're studying radiation problem, how the circumferential arrangement of the resonators affect the performance of your, I maybe missed this.
Okay. Yes. In fact, if all of them are identical, right?
Yes. You
arrange them. If all of them are identical, then you will have a single frequency that can be absorbed, and this frequency will not pass the bound imposed by the theory. However, if you want to do something that will be broadband, you can design, here you have a single ring with different Helmholtz resonators. You can see here the cavity are completely different one to the other, and also the necks. So first, Anton, did you understand my answer? Or?
Yes, yeah, I think, yeah, I followed you, yes. Yeah.
Okay. Apologize for my network problems.
I was also, I suppose, the question was also the distance between the circumferential distance between the resonators, but I can ask you that later, so okay. I don't want to take more time because there are more questions to answer.
Okay. In any case, the simulations are done by numerical finite element methods, but in any case, the theory is based on transfer matrix method. So the coupling is not too much important here.
Okay.
So the second question is, how did you solve the leaks, if any, in the experiment studied in the last system presented? Did you seal it in any way?
The what? Sorry?
Leak.
The leakage.
Leakage.
Yeah. Yes. In fact, there is not too much leakage in the problem. In what system? In this one, in the radiation, or in the other one?
You said in the last
part
experiment.
Okay, in the last part, you see here we have a source. The source has been introduced in a big cylinder in order to be isolated from the exterior. Then we have the tube, and then we have the radiation, right? In fact, for this panel, we have some finite length, and in the floor here, we put some foam in order to remove the reflection from the floor, but we didn't have too much problems of leakage in that kind of systems. It's more, in my opinion, the leakage is more important in the other configurations in which you can have some leakage from the sides of the structure. For example, here, here you can see that there are some small slits here. And in fact, in order to avoid the leakage through this, we use the grease. We put some Vaseline. Okay.
Yeah, thank you very much.
Did we answer a question from Rod? Are there any results of the transmission loss for the ring absorbers?
Look, in the ring absorbers, in fact, look, the absorption is defined as 1 minus the energy reflected minus the energy radiated normalized by the incident wave. So it's not a general absorption coefficient because here we have the radiation, right? So if we have alpha equals to 1, that means that these two energy should be very close to 0, right? Yeah. So in fact, I didn't plot the transmission loss in any configuration here, but in fact, here at these particular frequencies, the reflected energy and radiated energy are both very, very low, because if not, we cannot have a perfect absorption here. Right.
But the question is, these, I assume these are all numerical simulations. You haven't done any measurements for these.
Yes, yes. This is the green dots here are experiments.
Experiments, sorry, yes.
All the green dots in these configurations are experiments here.
Thank you. So that answers Rod's question. So the last question is from Arthur. Did you experiment with increasing the coupling of the resonators? This might be used to address the issue of a small resonator relative to the cross-section of the duct.
Yes, this is a very good remark. This is what I was saying previously here in this situation. if you model the system by using the coupling between resonators of the multimodal structure, you can see that when the resonators are very close one to the other, so when these systems are close to here, this means that the transmission loss is not so high. So that means that the transmission is quite big. So it's very difficult to obtain perfect absorption. And if you want to obtain it, what you need is to do it for a very narrow system. So in fact, when we optimize the structures, basically what we are doing is playing with the coupling of the resonators to obtain the perfect absorption. This is intrinsically introduced in the modeling of the system.
Yep. Arthur has asked another question. Thank you. He said, are there any differences between a square cross-section channel and the circular cross-section? Shall I ask Arthur to ask a variable? How can I?
With respect to the cross-section, the physics
circular. Is the difference between a square cross-section and circular cross-section?
Yeah, the physics is the same. You can do the same in both systems. As you can see here, we use for the last part we use cylindrical tube, but we could use also a square one. The physics is the same. You only have to take care of what is the modal expansion in each kind of tube, and what is the coupling with the resonators, and how you can do the multimodal matching. But basically, the physics is the same. There is not too much difference.
Right. Sorry, one last question, and I think I'll wrap it up. And Olga is asking, how important is baffle for the last problem? What if there is no baffle?
Yeah, that's a very good question. In fact, the baffle is important because we need to know what is the expression of the radiation impedance in order to treat the problem analytically and obtain at least some expression of that. If it's not buffered, you can obtain also you can use the same procedure by using the radiation impedance of the unbuffered problem, but I would say that you can do it in a same way, I guess. But you have to change the configuration. Is the only. But you can do it. There is no restriction on that. I have to think a little bit more on that, but I would say the only thing you need is the expression of the radiation impedance here, and if it's unbuffered, you have it also. So you can change this impedance here, and then you can redesign the structure by using the new expression and obtain the system.
Thank you. The two questions Jean-Philippe wants a question. Sorry, I'm allowing Jean-Philippe to talk.
Yes.
Please, Jean-Philippe.
I cannot see the
You're muted, Jean-Philippe.
Yeah, sorry. No, it was I'm not. I won't ask questions. Sorry.
Okay. Arthur, please unmute if you wish to ask a question, or yours have been answered.
Sorry, yes, I did have. Thanks so much for the presentation and answering the two questions. I did have one further question, and this is probably to the same point. So I can see this particular order of the resonators. They're not ordered in a kind of ascending size, or they're not ordered in ascending frequency. They seem to be kind of at alternating points where there's a small opening and then a large and then a small. Was that to do with the coupling between trying to achieve a full wavelength between peaks?
Yes. So yes, as you can. Yes. So there is a role in the order of the resonator. For example, here, as you can see, there are some small resonators here and some big resonators here. So these big resonators are imposed by the physics of the problem to be big in order to introduce low real part in the impedance of the second resonator to kill the transmission. This is what I was saying just here. We need a small value of Z2 to cancel T. And then we have to introduce some losses to cancel the reflection. So if the transmission want to be canceled in a big cross section, we need big resonators in order to have a small amount of impedance of losses in order to cancel the transmission. So all of that are due to canceling the transmission. And to introduce the amount of losses to absorb, we need to introduce a small resonator to increase the losses. So you have some part here that corresponds to the case in which we want to cancel the reflection, and the other part which corresponds to the system, to the resonators to kill the transmission. And both of them are crucial to obtain the perfect absorption. Then, how important is the position inside of this configuration? We don't have a clear answer. What we know is that they should work by pairs because two of them works. But when all of the structures, all of the resonators are put it together, as there is the evanescent coupling between the resonator, is difficult to see what is the relevance of the position of each resonator inside each of the two parts, right? But what is clear is that we need some part that cancels the transmission and the other part that cancels the reflection.
Well, thank you very much. I think we have answered questions, and I would like to thank you, Vicente, for interesting presentation, and and thank also our audience for their participation and very interesting questions. And if there is no further question, I will terminate the recording.
Okay, thank you all for the questions, and thank you, the UKAN, for inviting me to deliver this talk. It was a pleasure. Thank you very much.
You're welcome.
Thank you.
Thank you.
Bye. Bye, everyone.
Thank you.
Bye.
Bye-bye.